Right now we haven't touched upon sets. Those were also very interesting things that we have. And let's just write it to add an element in a set. So of course you can add an element in the set only if it exists. And if it does not exist, if the element exists, you cannot add it in the set. And that will exactly be what I will be looking at right now. Now the problem is I add if it is not already in the set, and we haven't touched upon not in Prolog, and that's a cheating I've been doing since the very first time. Determine the truthness of this, determine the truthness of this, determine the truthness of this. What if something happens when things are false? If X is not an element of the set, then you add it. If it's already there, 5 union 1, 2, 3, 4, 5 is 1, 2, 3, 4, 5. You don't add it. So now I need for the first time the not defined, and that's going to be interesting for the first time that I will have to write down with not. Now remember, Prolog is closed world assumption. So something cannot be determined or something fails, and false are equivalent. So let's model not. I say not is a function which takes a predicate as input, and if P succeeds, if P is true, then the answer is bound to fail. Then what I'll say is that I will bound to fail, otherwise I will say that it's true. So that's a little thing that I want to have. Now that's another problem that I have got. So I have this term otherwise which is added, and so far I did not have that. So first let's add otherwise, and then let's add this not. And we'll do it one after the other. So now the problem is a cut operator. The cut operator is given by an exclamatory. So far what we've done in English language, if premise 1, then consequent 1, if premise 2, then consequent 2, and so on. Now what we'll do is we'll model something which is practical in a lot of human problems, including many problems that we've seen so far. This is if premise 1, then consequent 1, else if premise 2, then consequent 2, else, so far, and finally otherwise, consequent n. So we said that the entire backward chaining is nothing but a and or graph. So this is the and or graph. And now we've got in special type of ORs, which are these ORs. So this if else, if said that multiple branches could be true simultaneously. This is also true, that's also true. Now we've got a special type of and or graph in which we have a constraint that only one branch will be true at any point of time. If the first is true, the second and the third will be false. If the second is true, the first and third will be false. If the third is true, the first and second will be false. And that is a heuristic that Prolog could use. Very good. And that is also a specification that I could use. Like here, I did not have any premise. It doesn't mean that there's no condition. It means that all these conditions should be false, and If all these conditions are false, then this condition is true. So these are things that we'll be modeling, or we'll be modeling for the exclusivity of the all nodes. That will help me two ways. Number one, as a heuristic, and number two, as a specification. So like last time I had to specify something I couldn't specify. So I'll specify it using this new constraint specification that the third branch is true if the first two branches are false. So I'll say if first branch condition, else if second branch condition, else whatever. There's no condition. It means just have the first two branches as false. At the execution time, it's also useful because when one branch succeeds, the other two are not tried at all. There's no need to try it out. Only when one branch fails is the second branch tried. So I'm not into a theoretical mood today. Let's directly go into and specify this thing up. So we need to do sets. So let me write down the condition over here. So let's write down add to set X over the set S. So let me draw the set S, of course stored as a list S, and of course it had a head and it has a tail. Should I add X to it or not? The answer will of course be X added on top. So X followed by the entire set S. That's my answer. If X is not a member of S, and the answer is just S. I like to draw the answer if X is a member of S. So let's write this thing down. So add to set S. Let's write down as the format we are used to, and then I'll do this thing. So I say if S X is a member of S, the answer is nothing but S, unchanged. If X is already a member of the set, then the answer is, of course, nothing but exactly the same S. Okay, there has to be an answer. So A is the answer. So the answer is nothing but S. Or of course it's obvious that I'm talking about the answer. It's all A is equal to. Otherwise the answer is X added on top of S if X is not a member of S. I just realized it's been a hybrid of functions and sets, so yeah, it was a bad explanation. Let me directly write it as Prolog. So X added to S gives the answer A. So the first condition is member X is a member of S, and if X is a member of S, then what happens is my answer A is equal to S, or I write it down in a short form. So I write it down A is equal to S right here. And now I can drop this and promote this over here. Read it as if X is already into S, then the answer of adding X to S is nothing but the set S itself. Obvious. So this, let me write it down as otherwise. So this is what I write it down as otherwise, and I say that this exclusion principle holds by this cut operator. So now I won't write down X is not a member of X, because this only holds good when this branch fails. I specified it with the cut. So otherwise, I won't write down anything over here. It's implied, it's cut, so this branch will only work, this OR branch will only work when this OR branch fails or when this condition fails, after which I apply the cut. So add, of course I need to write it down the other way around as well. The answer A will be, if X is not a member of S, I did not write down because it's exclusive. If this branch works, then this fails. If this works, then this fails. Or this condition is opposite of all the other conditions over which the cut operator was applied. So the answer is, of course, X added on top of S. And I write it up in the more interesting manner. So A is equal to X added on top of S. That's totally true. Then let's just write it down. Prolog add set X S S. This is true if member of X comma S. Mutual exclusion constraint, fact, the answer of adding X to S will be X added on top of S, of course, and there's no condition over here. This only succeeds when this condition fails. And you could write down the base condition if nothing is added on top of, okay, here X is not in this, so there is no base condition like that. Add S, 4 to 1, 2, 3. It gives me the result as the new set L, and of course L is 4, 1, 2, 3. It doesn't matter where you add. However, if I add 2, 1, 2, 3, no change. I get the same thing back again. So that's what is add unique, or that was the first set. You could extend add up to the standard little thing, which is append unique. Or to say the union. So let's do one simple little thing. So union of S1 and S2 gives me the set S. So of course I like to draw a lot of figures. This is my set. Oops, that's too large. So that's my S1 with, I'll recurse on it. So let's say head 1 and tail 1. This is my S2. Another set, I won't recurse on it, so I don't divide it into a head or a tail. And this will be my set S. So let's say head and a tail. And the appending, of course, will be similar to the list like this. And this time I only need to append unique. And in order to append unique, I need to make sure that anything which is, if it's already there, it's no longer what is repeated. And therefore let me take in two little cases. The first case is if H1 is already a member of S2. So all the elements of S1 are unique to itself. It's a union between two sets. All the elements of S2 are also unique to itself. It's by the set definition. So the first thing that I do is, what happens if the head that I am considering is already there in the second set? Now I don't need to consider H. So my answer will be nothing but everything applied on the tail itself. So I can just say my answer is when I do a union of tail 1 with S2, and the answer is this little thing which was S. So this S is the answer. That's the first condition. So union between H1 and T1 to S2 produces D, result as S. Now we'll also have to do it the other case, what happens when the element itself is, on the contrary, not a member. And whenever I say it's not a member, then do make sure that you do apply a exclusivity constraint. Why exclusivity constraint over here? Because anything before the exclusivity constraint is that uniqueness. So my condition of uniqueness is based on this. So my exclusivity constraint is also based on this. So otherwise, now I can be very sure, I won't write it down as a condition, that if not a member H1 comma S2, because this exclusivity constraint is there, so I can just draw it up and write down what will happen. So union of H1 T1 on S2 produces a result which is HT. So I'll just overwrite this thing. If H1 is not a member of S2, then H1 directly gets transferred, of course, over here. So I have H1 directly getting transferred. I won't write down H is equal to H1 and then cut it up. And of course, I won't write down not member H1 comma S2 because it's on the exclusivity over here. So I can directly write down that T is what is produced as a result of union of T1 with S2. And my base condition, a union between MT and set 2 is nothing but set 2. That's a fact. So let's quickly write that down over here. So I'll repeat it once more very quickly. The base condition, if I add the empty set over any S2, then I get the set S2. It's uniquely satisfied. On the other hand, if I take a union between some head 1, tail 1, and I add it to the set S2, the answer is a set S, where now I'll have to define the condition. So I say member X comma member H1 comma S2. So if H1 is actually a member, then the answer is nothing but a union between the tail of the first followed by the second set is my final answer. Otherwise, my answer is, so let's repeat this one up. My answer is given by a head and a tail, where the head is directly obtained from this, and on the tail I will use recursion to find out the answer. So union of T1 is 2 gives the answer T. So the answer T is defined by the union between T1 and S2. T is defined, or T, which is my final answer, is the union between T1 with S2. Let's do that quickly. Union of 1, 2 with 3, 4, and 5 produces a set S. And S is 1, 2, 3, 4, 5, of course. Let's say 1, 3. Answer is 1, 3, 4, 5, of course. 3 was repeated, it did not get occurred. So 1, 3, 4, the answer is of course 1, 3, 4, 5. And if you want to do it the other way around, so What is a set S? When added to 3, 4, 5, it gives you 1, 2, 3, 4, 5. Of course, it will go infinitely because there are infinite such sets possible. So because the answer is infinite, we will not take that up.